Hi group, today we're looking at rate of change. Now when you think of rate of change, you probably think about slope or you think about rise over run. Just want to suggest that rate of change is that and more. Let's have a look at a little scenario here. Got some pieces of equipment for measuring volumes, pouring solutions in a chemistry class. How could we use this equipment to demonstrate each type of rate of change? We have constant rate of change. So something is increasing or decreasing at steady rate, rather. Zero rate of change would be where something is at a state that's not changing at all. A negative rate of change where something is dropping or decreasing, and a varying rate of change where there's change, but the difference is not constant. So let's have a look at constant rate of change. Taking any of these beakers that have a uniform shape, the little one, the big one, and filling them up from another full beaker of either the same size or smaller size would accomplish that constant rate of change, provided we poured it at a constant rate. Now, if we weren't able to do that, we could attempt to pour it at a constant rate by putting a funnel maybe in the path so that at least the diameter of the opening here is constant, and we could assume that the flow rate would be pretty constant. So we could accomplish constant rate of change that way. Zero rate of change is pretty simple. Just leave something to remain empty, remain full, or remain in its given condition, and you have zero rate of change. Negative rate of change. All right, well, filling something obviously increases the volume. So to get a negative rate of change, we could either empty something, or we could look at it a little differently. Maybe we take our funnel and we're looking at filling up the graduated cylinder. But this time, instead of looking at the volume that we've added, let's look at the volume that remains. So if we were to take a little beaker and pour the contents of a little beaker into the funnel, then as the water level rises, the volume increases, but the amount that remains is going to certainly be shrinking at any given time. Okay, so that would be negative rate of change. Varying rate of change probably could be accomplished by pouring something at a non-constant rate. So maybe taking your big beaker and pouring a little bit at a time and then gradually increasing the amount that flows, and you'd probably achieve a varying rate of change. Another way would be to use something that doesn't have a uniform diameter. So if you consider the conical flask has a lot of volume towards the bottom that has to be filled up for a given diameter. But as we move our way up the flask, the diameter gets smaller and smaller, and so the volume that we're going to be able to add for a given flow rate will increase. As we get up into the neck, it'll rise faster and faster. So that would accomplish a varying rate of change. So these examples, just to get you to think about things that aren't changing at all, things that are increasing, things that are decreasing, and things that are changing but at a variable rate. So when we go back to our handout here, you have your handout, and we're looking here at just filling in some of the information here. Change, when we talk about in math, is using the difference operation. So change is calculated using the difference or subtraction. Sum uses addition, change uses subtraction. Specifically, the second value subtract the first. Now, when we look at rate and rate of change, we're often with rate just relating to quantities in a ratio. With rate of change, we have two quantities which themselves have differences. So it could be differences in time on the road for how far we've driven down the road. Could be differences in time elapsed for a sprinter running down a track. It could be differences in how much we've worked in hours and how much money we've made. It could be differences in how much fuel we consume in a race car for every minute that it's on the track. Could be differences in density of a liquid as it cools, in how much weight is occupied in a given amount of volume. So all of these units remind us that rate of change, we're not just comparing quantities, but we're comparing quantities with units. When we look at linear relations, rate of change is usually associated with a calculation of a change in y to a change in x, or a difference in y for a difference in x. Rise and run are fairly appropriate, but sometimes the slope of the line is negative, and vertically we don't really rise at all. We drop, but rise can be positive or negative. The horizontal run typically is positive as we move from left to right. So when you are calculating rise and run from 2 points on the graph, remember that x and y coordinates are coming from the axes, and we've got to remember the first coordinate's the x, second coordinate is the y. When we calculate them, typically the first point is to the left and it has coordinates x1, y1, and the second point is to the right and it has coordinates x2, y2. So in this case, y2 subtract y1 would be 3 subtract 7. So the rise would be -4 units. The run would be 4 subtract 2. So here this graph is dropping at a rate of 4 units for every 2 units in the x direction, or -4 for every 2 is the same as -2 for every 1. So the unit rate would be -2. When we look at a table of values, we can calculate the same thing we do in a slope calculation. Numerically, we're still taking the numbers in the y column and subtracting second, subtract first. Same thing for the x. We want to make sure that we have a constant increase in the x value in the first column. It doesn't necessarily have to be 1, but we need to take it into account if it's not 1. If it's 1, dividing by 1 isn't going to change our rate of change value, but if the increase is 2 or more, or anything that's not a unit, we would need to divide by that run value. Okay, so a differences table has a third column, and we are calculating rate of change in that third column. First differences are the changes in y, and second differences we can use if we want to identify something as being nonlinear. So as we go further down here, when we calculate rate of change for lines, we would discover that all lines have a constant rate of change. The first differences will always be equal. The line visually will have a constant slope, which is a description of the steepness as well as the direction of the line. In this example here, slope of -3 means that y drops -3 units for every 1 x unit, which implies that it's fairly steep and it is decreasing. The negative sign controls the direction of the line. Horizontal line has a flat slope. It has a 0 rate of change. The first differences in the slope will both be 0 as well. When we look into the nonlinear, anything that's not straight line is described as nonlinear. The rate of change is varying. The first differences will not be constant, and the slope will change. Typically for nonlinear relations, we can analyze the rate of change, but we would call it average more appropriately, because from point to point, the slope is not constant. So neither is the rate of change. So from 2 different points on a curve, we could look at a graph that had, let's say, exponential decay as the trend, and if we were to identify points on this graph, we could identify pairs of points, and in between any 2 pairs we could calculate a rate of change by connecting these with a line. We kind of get an idea of what the slope looks like between those 2 points, and we see the slope is getting less and less negative. And so clearly here we can't call the rate of change constant, but we can say on average between any 2 points, it's represented by that value there, which would be still requiring us to take y2 subtract y1 and divide x2 subtract x1. Okay, that's all that really needs to be reviewed for this first video lesson. In class, we're going to be working on some group work with 5, 6, 7, 8, or 13. As a whole class, we're going to go through number 9 using the graphing calculator to see how we can use technology to create differences tables and calculate rates of change for us to identify linear and nonlinear relations. And we'll do a little bit of regression with that. And then independently, I'm assigning 10, 11, and the other question of 8 or 13 that was not done in groups. We'll see you tomorrow.